Okay, welcome back everyone. So we are back to talk about solution sets to linear systems. And you might be thinking, we've already talked about solution sets of linear systems. It was kind of the first couple of lessons that we had. What we're going to focus on today is mostly the case where you have infinitely many solutions. And that's a case that we haven't discussed very much. So how do you know when you have infinitely many solutions? How do you write the solution set? What does it mean in terms of vectors and linear combinations and stuff like that? So that's what this is going to be about. So let's go ahead and get started. Solution sets of linear systems. Okay, so first of all, a couple of things that we have said. We've said that every linear system can be written as AX equals B for an appropriate matrix A, an appropriate vector X, and an appropriate vector B. Every linear system can be thought of in that way, in terms of matrices and vectors. We've also said that a linear system is going to have one solution, no solutions, or infinitely many. And when there's infinitely many solutions, that happens because there is at least one free variable. You remember we talked about free variables and basic variables? I guess this is a course that has a lot of definitions, a lot of terminology. You might find it helpful to do something like flashcards. I think if I were a student taking this class, I might consider doing flashcards, like to know the definition of free variable, basic variable, linear combination, span, some of those things. And some of the things we haven't gotten to yet. All right, let's talk about, here's another term. This is a new term for us. Homogeneous linear systems. Homogeneous linear systems. And these are systems of the form AX equals 0, the zero vector. That is what a homogeneous linear system is. It's just the right-hand side is all zeros. And we're going to talk about these for a little bit because these come up a lot. I'll tell you a couple of facts. A couple of facts about these. Number one, a system of this form always has at least one solution. Remember, when we say solutions, we're looking for the x's. The x's are the unknowns. In general, when you have a linear system, there's some unknowns like x1, x2, x3, and we're making them a column of x's, and we're calling it the column vector x. So now, in this homogeneous linear system, we have this vector x that contains all of the unknowns, all of the variables. I'm saying there always is at least one solution. Can you see what the one solution is? How about the zero vector? That will always work for systems of this form. Now, there might be other solutions. Okay? But, up above, we said there's one solution, no solutions, or infinitely many. And so far, what I'm saying is that for a system of this form, you're guaranteed to have at least one solution. And the name for this is called the trivial solution. We say that you always have at least the trivial solution. Fact number 2. Ax equals 0 has non-trivial solutions if and only if there is at least one free variable when solving. Okay, so we do have to go through the process of trying to solve it, and we are interested to see if there are going to be any free variables. And when we get to the end of it, we're going to have to figure out how do we write the solutions, like what's a nice way to write them. So let's go through an example. Solve. I'm going to talk us through this. It's going to be another linear system. This is going to have 3 equations and 3 unknowns. This symbol I'm writing, I want this to be a minus sign. 3x1 plus 5x2 minus 4x3 equals 0. Minus 3x1 minus 2x2 plus 4x3 equals 0. Next line, 6x1 plus x2 minus 8x3 equals 0. Put a bracket to the left of that to make it a system. Let's talk about this. Okay, first of all, I'm going to say that note that this is in the form ax equals the 0 vector, where A would be just the coefficient matrix. It would be 3 by 3. And x, what would x be? X is a vector containing x1, x2, x3, period. And in this context, the 0 vector would be the column of all zeros. In particular, it has 3 entries, and they are all 0. So I think when we introduced the 0 vector in a previous lesson, we said that it's a column vector, and that the size of it is usually clear from context. So I think that because of the size of A and because of the size of X, it's clear that we're talking about 3 zeros here. You could see them on the right-hand side. By the way, A is a 3 by 3 matrix, and because of that, sometimes we might refer to this as a 3 by 3 system. 3 equations, 3 variables. So if you ever hear me say like a 3 by 3 system or a 2 by 2 system, you know, I might be talking about the size of the coefficient matrix. Anyway, how do we solve this? We solve it with Gaussian elimination on the augmented matrix. So let's set up the augmented matrix of the system, which looks like A, but also has that additional column of zeros. That's the one that we really work with. 6, 1, negative 8. Let's double check. Does everything look good there? Okay. Sometimes when you're copying things from one place to another, take some time to just double check everything. Because if you like get one minus wrong, or you get a minus wrong or a plus wrong, or a number wrong, it can change everything drastically. But I think this looks good. I would like to do row reduction on this, and I'm going to say that at this point, we've done row reduction often enough that I'm going to go through it a little quicker. You know that there's some flexibility as to which row reduction steps you do in which order. So you could even solve it in a different way. You should still get to the same answer. What I'm going to do right now is I'm going to do 2 row reduction steps at the same time. And I'm going to tell you it's okay to do that as long as you're careful. I'm going to add R1 to R2. and I'm going to add negative 2r1 to r3. And those two steps are kind of independent of each other. I'm doing something to row 2, I'm doing something to row 3. There's no reason I can't do them at the same time. Let's copy row 1 because row 1's not changing. Okay, now we're going to change row 2. When I add r1 to it, you know, I'm doing that because the 3 plus negative 3 is going to get me a 0 here, and then the rest of it winds up looking like this. When I do negative 2 times row 1 and I add that to row 3, I'm going to get a 6. Oh, sorry, not a 6. We had a 6, and that 6 is going to become 0, and then I have negative 9, 0, 0. I have an idea for step. I see a 3 and a negative 9, and I'm thinking it would be nice, we could like get rid of that negative 9 by adding, watch this, add 3r2 to r3. So top row stays the same, row 2 stays the same, row 3 becomes all zeros. Now, technically, this matrix that I just arrived at is in row echelon form. It is, you know, what we just did was Gaussian elimination. This is not reduced row echelon form. We'd have to go a little further for that to happen. But, you know, we can see the pivots, the pivot positions where this 3 is and where this 3 is. Oh, by the way, we have a free variable. Free variable is happening right here. X3 is free. Because ordinarily you expect, you know, column 3, row 3, you expect something here to tell us what x3 is equal to. But we just have a row of zeros. So we're not getting any information on what x3 is supposed to be, so x3 can be anything. I'm going to keep going with this row reduction. Let's keep going with, you know, Gauss-Jordan elimination is when we go further and try to get it into reduced row echelon form. And I like that because once we finish that, we kind of get all the answers. So, yeah. How about we do something about the 3? Let's do R2 times 1/3. That's going to clean it up a little bit. 3, 5, negative 4, 0, 0, 1, 0, 0. I like that. Trying to turn the pivots into ones. I should say the leading entries of each row. I'm trying to turn those into ones. How about so we have a choice here. I could multiply the first row by 1/3. That would change the 3 into a 1, which would be nice. But I'm thinking about doing that, and I'm saying, oh, then I'm going to have like a 5/3 and a negative 4/3, and that's really messy. So sometimes I try to do these in a way that avoids fractions, if possible. If possible. I mean, we might not be able to avoid fractions altogether. The answer might have a fraction in it. But my idea is, instead of multiplying row 1 by 1/3, how about instead I focus on getting rid of this 5? I want that 5 to become a 0. So I am going to add negative 5 R2 to R1. Okay, let's just do that step. 3, there, like that. Well, now I'm at this step where I think, okay, you know what? That idea that I had earlier to multiply by 1/3, I think we have to do it. Let's do row 1 times 1/3. The one good thing, though, is at least we knocked that 5 out of the picture. We turned it into a 0, so I'm not going to have like a messy 5/3 to deal with. We're just going to have a 0 in that spot. We will have a negative 4/3. But look at this. We've got it in reduced row echelon form. Reduced row echelon form, also known as RREF. That is the end of Gauss-Jordan elimination. We have all the leading entries are 1s. Any row that consists entirely of 0s is at the bottom. All of the leading entries are in this sort of staircase pattern, and also all the entries above and below the leading ones are 0s. Everything below this one is a 0. Everything above and below this is a 0. We're done, but what can we say the answer is? What can we say the answer is? Well, I said a minute ago that x3 is free. So that's one thing. What is x2? We try to read the equations from the bottom up. So the bottom equation doesn't tell us anything. The second equation says 0x1 plus 1x2 plus 0x3 equals 0. So that entire thing translates to say x2 equals 0. Here's what I'll say. We're doing this by rows. What does row 1 say? Row 1 says x1 minus 4/3 x3 equals 0. So can we solve for x1? Well, yeah, we could solve for x1 in terms of x3. We could say x1 is 4/3 x3. But that's nice because we like to solve for basic variables in terms of free variables. So having x1 in terms of x3 is good. Now, we had a couple of problems like this, I think, in previous lessons, but there's a particular way that I would like us to start writing the answers, the solution set. I'm going to say solutions are of the form. Now that we understand that x can be thought of as a vector, I'd like to write it as a vector. X is equal to, and I'm going to put in what we found for x1, x2, and x3. 4/3 x3, 0, x3. I'm going to do one more thing with it, though. But just before I do one more thing and put a box around it, just take a look at that and make sure that makes sense to you. Okay, solutions are everything of that form, or a new way for us to write this is x3 is just a real number, right? I mean, x3 can be any real number, but real numbers you're allowed to pull out of a vector. So we could write the x3 out front, and then inside we can write 4/3, 0, 1. And this is a nice way to write the solution set. If we want to, we could also say, like, for all x3 in the set of real numbers. Any real number x3. So what's nice about writing the solution set this way? So we found infinitely many solutions. Okay? When I write it in this manner, what's nice about it is it kind of shows me that solutions to this system are any scalar multiple of this vector. Here's a vector, 4/3, 0, 1. Take that vector, multiply it by any real number you want, you've got yourself a solution. x3 could be 1, x3 could be 2, x3 could be a million. As long as you're multiplying it by this vector that we found, you've got a solution. So we did answer the problem, but I want to say a little bit more about the solution, because this section is all about solution sets. So note, this answer that we found can also be written as x equals the span of this vector. Maybe we should think about this before we move on, okay? Why is span showing up here? Wasn't span supposed to be the set of all linear combinations of something? Why are we talking about linear combinations now? Well, is this thing right here that I'm pointing at, is this a linear combination of this vector? Well, yeah, it is. It's just usually when we talk about linear combinations, we usually have like a bunch of vectors, v1, v2, v3, whatever. Here, we only have one vector that's going in the span brackets. If you only have one vector there, and you say span of one vector, you're basically just talking about that vector with a weight out front, right? We use the word weight, or you could just say with a scalar out front. So yeah, x equals every vector that is a multiple of this, or x equals x3 times this, where x3 is any real number. They mean the same thing. I have a fact to tell you that goes beyond just this problem. Fact, the solution set of a homogeneous system. I'll remind you what that means. That means the right-hand side is 0. Ax equals 0 can always be written as x equals the span of v1 dot 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 vp for some vectors. And I'm going to put the s in parentheses for some vectors. It could just be one vector, or there could be more than one. I used the word always, and in math, when we use the word always, that's kind of a strong statement. It's kind of nice to write the solution set. Here, I'll put a box around this too. It's kind of nice to write the solution set in this way, because, you know, we're trying to describe a family of solutions, and this shows us the structure of those solutions. It's like, what are the solutions to this system? Well, answer, any multiple of this. Any multiple of this. That's your answer. Or maybe if there's some other problem, maybe we might have to say that it's any linear combination of these, you know? Now, I use the word always, so you might say, wait a second, what if there's only the trivial solution? Does that still work? Because I used the word always. What if it's only the trivial solution? So if the only solution is the trivial solution, x equaling the 0 vector can be written as span of the 0 vector. So what we said above still applies. It might seem a little silly, because why are you saying, you know, okay, so the solutions are any multiple of 0? Any multiple of the 0 vector? Well, any multiple of the 0 vector is the 0 vector. Okay. But the point is that it's okay to use the word always up here. You have a homogeneous system. Solution set can always be written as the span of something, even in the trivial case. So, so far in this lesson, we've talked about systems where the right-hand side is 0. Let's talk about other systems. Okay. Other systems where the right-hand side is not all zeros, we can now call non-homogeneous systems. So this is AX equals B, where B is not equal to the 0 vector. Now, the vector B might have some zeros in it. That's okay. We're just saying it's not all zeros. Now, we have seen, we've already seen some, non-homogeneous systems. So, example 1. From the first lesson that we had, we saw this system. That's a 2. 2x2 plus x3 equals 4. 3x1 plus 8x2 plus 7x3 equals 20. 2x1 plus 7x2 plus 9x3 equals 23. All right, if that looks familiar to you at all, I think that we have seen that. And we found that x equals, we had a unique solution. I'm now writing it as a column vector. I think that when we found it back then, we probably wrote it as coordinates. Right now, at this point in the course, we're more interested in thinking of things in terms of column vectors. So this has one unique, non-trivial solution. Also going to say, note, 0 is not a solution. So what I want to say about this is that at the beginning of this video, I reminded you that every linear system, there's 3 possibilities for a linear system. You have one solution, no solutions, or infinitely many. For the discussion of homogeneous systems, we said you always have at least one solution. So you have one solution or infinitely many. In the case of homogeneous systems, if you only have one solution, it must be the trivial solution. Okay? You can't have like one unique solution that's something else if it's a homogeneous system. Now, for the non-homogeneous case, it is possible to have one unique solution and it's not the 0 vector. Okay? We've seen some other examples too. We've seen other systems where the right-hand side is not all zeros. So, example 2. I think this was from our second lesson. From our second lesson this semester. I think that we had one that was 3x1 minus x2 equals 6. And the next line, minus 6x1 plus 2x2 equals negative 12. So I would call that a 2 by 2 system. And we found, I'm skipping the work because we did this already, but we found x1 equals 1/3 x2 plus 2, and x2 is free. And I think that back then we wrote the solution like that, or as coordinates. 1/3 x2 plus 2, comma, x2. That is a small system with infinitely many solutions. The solutions are of this form. This solution set can also be written as, now that we have a better understanding of vectors, and we are thinking that the unknowns that we are solving for, they make up a vector x. So what would I say the vector x equals in this case? What do you think? I could take the coordinates from this. When we wrote it out as something comma something, we could write, you do this 1/3 x2 plus 2 and x2. That's one way to write it. I'm actually not going to circle that yet because I want to do something else with it. In that thing that we had above, I guess it was a few minutes ago by now, but we had homogeneous problem and we pulled the x3 out. I kind of want to pull the x2 out. If I pull the x2 out of this, I have to be careful about how I do it, right? Because this first entry has an x2 attached to part of it, but then there's this plus 2 that's just kind of floating there. So here's how I'm going to write it. The vector 2, 0 plus x2 times 1/3, 1. I'm going to circle this and say that this describes the solution set, and we could say for all x2 in the set of reals. Like x2 can be anything. So what do you think? Is this a nice way to write a solution? I think this is a nice way to describe the solution set because, again, there's infinitely many solutions to the system, but by writing it in this way, we get to see some of the structure. We get to say that every solution to this system is the vector 2, 0 plus a multiple of the vector 1/3, 1. And if you said to me, like, tell me 10 different solutions to this system, I could tell you 10 different solutions to the system. I would just put in 10 different things for x2. It would be easy. So this is nice. And a little later, we're going to see, later in the course, we're going to see like there's some significance to these two vectors. Okay? But for now, they do kind of describe the structure of the solution set. So when we have a solution set written in this way, we say this solution set is in parametric vector form. And this is the preferred way of writing solution sets right now. That's one example of parametric vector form, but let's get a little more general about it. So in general, parametric vector form can be it can be x equals a constant times a vector. It can be x equals a vector plus a constant times a vector. It can be x equals a constant times a vector plus constant times a vector. If I say etc., do you think that, can you see the pattern that I'm getting at here? I'll say where u and v are specific vectors, like above. The specific vector 2, 0, and the specific vector 1/3, 1. And S and T are free numbers, sometimes called parameters. So that is why this is called parametric vector form. It's a way of writing a solution set as a combination of parameters and vectors. Parametric vector form. So I'll give you a minute to see all that before we move on. Okay, so we're about to continue. We still have more to do. I just thought it would be a good place here to take a quick break. And I just kind of wanted to address one thing before we move on. The previous video that we watched, I think, was kind of a tough section. Even the one before that had some tough stuff with linear combinations and span. So if you're getting overwhelmed, I just want to remind you that these videos are really, they're not meant to be watched back to back to back. Okay? This isn't like something that you're gonna binge watch on Netflix. Taking a math class, you're really supposed to take the lessons one at a time. And what I hope you're doing is you watch one video and then do some practice problems, do some reading, do some homework, and try to absorb as much as you can. Take notes while you're watching the videos, so you review your notes, go back and watch parts of the video again if you need to. So really try to absorb everything you can from each video before you move on to the next one. I just wanted to jump in here and say that in case I haven't said it yet. I think that if I were a student, it would be overwhelming to just try to watch these back to back. You need to take time to try problems on your own, and then everything will kind of click. And also ask me questions when you get stuck. Okay? All right, let's get back to it. So if we understand what parametric vector form is, then I'd like to give you a problem to try. So example, I'm going to ask you to find the solution set in parametric vector form. For ax equals b, given a equals 3, 5, -4, -3, -2, 4, 6, 1, -8, and b equals the vector 7, -1, -4. Before you take a minute to work on this, let me just say that we did a similar system earlier, but that time the right-hand side was all zeros. Okay, so we did that earlier and we wrote that solution in parametric vector form, but that time the right-hand side was all zeros. This time it's not. So you need to solve the system, and then you also need to figure out how to write the answer in the correct form. So I suggest that you pause the video, spend a few minutes, and see what you can get for this, and then check back with me. All right, so we're getting lots of good practice in for solving systems. You see that a lot of linear algebra is about doing row reduction. So let's write the augmented matrix of the system, because I think that's the version that we really want to work with. So I'm going to say 3, 5, -4, 7, -3, -2, 4, -1, 6, 1, -8, -4. There's the augmented matrix, and we'll do some row reduction steps. Remember that there is some freedom of which steps you want to do first. Ultimately, we kind of know what form we want to get this in. Like I don't like this 6 being down here. I want to get rid of that. Maybe we want to get rid of this -3. You can do steps in different order, and we can still wind up at the same place. Okay, so don't worry if your steps were different from mine. I decided I'm going to do two things here. I'm going to add R1 to R2, and I'm going to add -2 R1 to R3. Okay, that's going to get me 3, 5, -4, 7. We're keeping that. Then we get a 0, 3, 0, 6, 0, -9, 0, -18. So that first step that I did, or really I kind of did two steps in one, I think that's the same thing I did on that earlier problem when we had this, but with the right-hand side equal to 0. That was the step that seemed like it made sense to me at the time, but that was also the step that seemed to make sense here. And maybe follow some of those same steps if you want. Here I decided I see a -9, I see an 18, I see a 3 and a 6. Like some of these things we could multiply by constants. How about this? Let's do R2 times 1/3, and let's do R3 times 1/9. That's not even how I did it in my notes, but I just, this is standing out to me right now, and I just want to do it this way. I'm doing that because then in my next step, I think I'm going to add row 2 to row 3. So add R2 to R3. Should we do anything else while we're at it? We could do something else. We could, how about we add -5 R2 to row 1. All right, so row 1 is going to change as well. How about we do the row 2 is staying the same. Row 3 is becoming all zeros. And now let's figure out what I'm doing to this row up here. I guess the 3 is going to stay a 3. The 5 is going to become a 0. -4 is going to stay -4. And the 7 is going to get -10 added to it, so I get a -3. Okay. What do we need? One more step to get into reduced row echelon form. Let's go ahead and do R1 times 1/3. And this is going to get me 1, 0, -4/3. Hey, that sounds familiar. And then it looks a lot like what we got earlier when we had a problem like this, but the right-hand side was all zeros. This time, the right-hand side was 7, -1, -4. We have this other stuff here. So we're in reduced row echelon form. From this, I can tell that x3 is free. Let's try to figure out what what the solution set is. So over here, I'm going to say x3 free. Let's work our way up and then say, what does row 2 say? Row 2 says x2 equals 2. Can you see that? Row 2 translates to just x2 equals 2 because it says 0x1 plus 1x2 plus 0x3 equals 2. What does row 1 say? I guess it says x1 minus 4/3 x3 equals -1. I'd like to solve for x1, so let's just move some things around here. Let's write this as -1 plus 4/3 x3. That's better because it says x1 equals. So, we kind of found x1, x2, x3. We would like this to be in parametric vector form. The setup that we want for parametric vector form in this case, I think we have one free variable, but there's also some other stuff. Maybe something that could help you. I wasn't planning to do this originally, but maybe something that could help you is just copy what you have for x1, x2, and x3. So like x1 looks like this, x2 looks like this, x3, we'll just write x3. I wasn't planning to do that step, but because that's not the finished answer. But maybe that can help you to see that this can be broken up into a vector plus x3 times another vector. Now, can you see what needs to go into these two vectors? We could take everything that's attached to x3 and put it in the second one. So there's like a 4/3, so 4/3 over here. How many copies of x3 are in the second entry? I guess 0 of them. And then how many copies of x3 are in the final entry? I guess 1. So that's part of the answer. And then this first vector is going to have everything that was not attached to an x3. So that's where the -1 goes. That's where the 2 goes. And the final entry just gets a 0. And you can verify that these two things are equal to each other. That the one vector here equals this vector plus x3 times this. I'm going to circle this. This is my parametric vector form. I think this is the third time today that we've written an answer in parametric vector form. And you know how when we write these, usually I've been writing on the bottom, I've been saying for all x in R, like for all x in the set of real numbers. And I'm going to tell you now that you could write that if you want, or you could leave that out. It's basically implied when we write a solution this way that x3 is free. So I'll put it in parentheses this time. I'll say for all x3 in R. But I think from now on, I might just skip writing that. It's optional. It's just kind of, it's implied by this form. Not just that x3 is real, but that x3 is free. x3 can be anything. All right, now I've got something for you. So I told you that earlier we did a problem like this, except the right-hand side was all zeros. This time we did this problem, the right-hand side was given, it was something else. Real quick, I just want to show you the previous page. When we did that other problem, when we did that other problem, this was the answer. This was when the right-hand side was all zeros. We got x3 times this vector. Look what happened now. We got x3 times this vector showing up as part of the solution, but then there was this other stuff here. And that's not just a coincidence. That's not just a coincidence. So when something in math is not just a coincidence, sometimes it's a theorem. So theorem 6. Suppose x equals p is a solution to ax equals b. Then the solution set of ax equals b is the set of all vectors of the form x equals p plus v with a little h next to it. So that's a lowercase v with a subscript lowercase h. Where VH is any solution to the homogeneous equation. AX equals 0, 0 vector. I'll tell you that the use of the letter P, the use of letter P here, you could think of it as P stands for particular. P is a particular solution. So suppose X is a particular solution, like one specific solution, to AX equals B. Then the entire solution set to AX equals B is going to be that particular solution plus any solution to the homogeneous equation. And that's why over here we had a particular solution plus all the solutions to the homogeneous equation. I'm going to write underneath this some of what I just said out loud. So in our examples, x equals -1 to 0 is one solution to AX equals B. The set of all solutions is that particular solution plus x3 times 4/3, 0, 1, where these were the solutions to the homogeneous version of the problem. Let me ask you, is there some, like, is this totally a surprise? Is this totally a surprise to us that this is true, that this happens? You know, we looked at a problem where we had the right-hand side equal to 0, and then we looked at a similar problem, but the right-hand side was non-zero. Similar problems have similar solutions. So maybe that is a simple statement. I don't know if that's always true in math, but similar looking problem, similar looking solution set. I also think that we could say that when we went from the homogeneous problem to the non-homogeneous problem, what did we change about the problem? We changed the right-hand side only. It's like we shifted the right-hand side. Instead of being 0, 0, 0, it was 7, -1, 4. We shifted the right-hand side. Shifting the right-hand side had the consequence of shifting the answer by some amount. It happened to shift the answer by -1 to 0. All right, so the two problems are closely related. Yeah, two problems are closely related, and in fact, the row reduction steps that we did were very similar, or maybe even they could be the same, because ultimately you can do the same row reduction steps to get it into reduced row echelon form, because whether the right-hand side is all zeros or whether the right-hand side is something else, same row reduction steps are going to work. Okay, so that is probably it's probably a good place to stop. So let's wrap things up here. Okay, so hopefully this lesson helped you maybe have a different perspective on systems that have infinitely many solutions. We see that we can write their solution sets in this form called parametric vector form, which kind of reveals some of the structure behind the solution set. Where we're headed next is, I think the next lesson will be about a topic called linear independence. Haven't talked about that yet. I would say it would be a good idea to go back and maybe review the definition of linear combination. Make sure that you feel good about what it means for something to be a linear combination. That's going to help you with the next lesson. Okay, so that's it, and I'll say take care, and I will see you soon.